All right, so the first thing we're going to do if we want to make an image geometry like we saw where we're sampling an image, you don't need to do this, but I kind of like this. It just like helps me get my head straight, sort of visualize what the geometry should look like, is to actually load the image into Rhino. So in that image I have there, sample image, it's in the Dropbox folder in today's lecture file if you want to use it. This one here, or you can use like whatever image you want. Grayscale will work better for this, but it can be color as well. So what we're going to do is we're going to type in picture frame and in Rhino, and then it's going to bring up a dialog window here. It's just going to ask you to navigate to an image. I think JPEGs and bitmaps. Pings work as well. TIFFs, I usually use JPEGs. So sample image here. And so essentially what I'm going to do with this is I'm going to place it, one of its corners at the origin. And this is just going to make it easier for us, and you'll see why in a bit. You don't have to, you can place it anywhere, but I'm just going to type in 0, hit enter, and that's going to place that one corner at the origin. And I'm going to hold shift, and this will snap it to the orthogonal, and I'm just going to drag out to really whatever. But if you're following along, just make sure it looks like this. So I'm holding shift to keep it snapped. And then you should see something like this. Now, you can leave your image this opaque. If you want to, though, if you're in the Rhino 1 course, you might remember when we were sort of taking sections of a building and modeling that building, we would take our picture frames like this. We'd go to Properties, Material, and then we would go to Transparency, and then just bring it up to whatever we wanted. So in this case, I'm just making a little, like, you know, it looks like 30% opacity. So, yeah.
I got the picture in.
That means that someone might have copied or cut the image out of Dropbox. What you probably want to do is just copy it to your desktop. Yeah, so if you see that, so like, let's say we save this. Here, actually, I'll just grab a new image. So I'll look up cute dog. Aww. And yeah, and this will be the rest of the class. Okay, I'm just trying to find one that works good for grasshopper, right? Actually, okay, let's okay, how about this pug? Pugs are kind of like ugly cute, but okay. So we're gonna save this pug. Cute dog eyes. Okay, so let's say, for instance, that I am placing this file. So picture frame, I'm navigating to my desktop to put in the pug. So I'm placing it like that. And now I save my file. So I'm gonna just save this on my desktop again. Pug, like so. I exit Rhino and I cut this window or this file and put it somewhere else. So I'll just put in my documents here. When we open Rhino, it's just like a broken link in InDesign or whatnot. It's just going to give you that white screen. So you see pug. And at least it should, we'll see. Yeah, so you'll get this. Image not found, that. So you just need to refine that image if you get that, or locate it somewhere where you can. And rather than working with some boring grayscale topo, I'm going to work with this cute pug for the rest of the class. Okay, and if you copy it back there, it should, if I just go revert, it should update now. And there he is. So, if you have an image like this, one thing I like to do for this, you can base off different colors, but I like to make these images grayscale, and you'll see why. So if you don't know how to make something grayscale, it's easy enough. Just open Photoshop. So I'm going to open the pug file, image, mode, grayscale, discard the color information, and there we go. So I'm just going to save it like that. Cute pugs and costumes wallpaper for.jpg added to your folder. So someone else is following along with a cute pug. Okay, so we have this pug here. Oh, don't. So our material, I'm just going to set the transparency up to like 70 or whatnot. Okay, so now we go into grasshopper. So I'm just going to type grasshopper into my command bar. So close that. Close. Perfect. Okay, so we're going to reference this picture frame as a surface. So with picture frames, you can see it is a surface. One surface added to selection. It just has a unique material applied to it. So to reference the surface, we're going to go to the parameters tab, geometry, and then surface. Put that down on the canvas, right click it, set one surface. So once we do have this surface, usually I like to turn this preview off, because we know that this surface here is this grasshopper surface. So with that, we're going to generate a grid of points on this surface. So I'm pretty sure we've used this component before. It's easy enough. It is under the surface tab, or yeah, surface tab, utilities, and then divide surface, so you can see generate a grid of UV points on the surface. So like that. And now what we want to do is we can just grab a slider so we can just adjust this. So right now they're both set at default 10. We're going to grab a slider so we can increase the density or decrease the density of these points. So that's under parameters, input, number slider. So I'll just make 2 of these. Actually, I'll edit it first. So again, review, to edit a slider, double click on the little slider tag here. Since we're dividing a surface, we can't have 1.5 U sections, so we're going to switch to integers, so we have whole numbers. Our min, we're going to say minimum of, I don't know, 2. Our max will say for this 50. It can be whatever number, it kind of makes sense to you. Click OK. And now I'm just going to copy this slider, so Control C, Control V. I'll plug the first one into U. And the other one into V. And actually, as I was sort of grabbing the wrong thing right there, if you need to adjust the resolution of your slider, so sort of, it doesn't really matter for integers, but let's say your slider is really tiny and you're having a hard time picking like an exact number, you can always expand it out, and this makes it easier to hit an exact number. Or you can always double click in, not the title here, but in the slider itself, so like right here, and enter in a number as well. So 12, confirm, good to go. So yeah, now we have some points like that. And I'm just going to save this file in the Dropbox as well for anyone if they want to catch up at any time. So March 16th. Perfect. So essentially the way image sampler works, that's the component we're going to use, is it's going to sample this image based on some value. So you know how in an image, an RGB image, there's certain things. So there's our R value, red, green, and blue together, like 255, 255, 255 equals white, 0, 0, 0 equals black. We can also measure brightness, as well as some other things. So image sampler, what it does is it takes this image and it samples those values at these points to return a number. So we're gonna see how that works. So, and the reason why I like choosing grayscale is it's really easy to do brightness. It's 0 is black, 1 is white. So what we want to do is we want to go to parameters, so this first tab here, input, and then image sampler. And it's going to look like this. You need to plug points into it, like so. So we'll plug our points into there. We can flatten our points if we want to. If we want to keep them, you know, in different groups for some reason, we can. So we all kind of know what flatten is now, so that's good. Maybe just a quick review. So if we don't flatten, so this is a pop quiz, a verbal pop quiz for all of you. So you can see here that I have 3 branches, 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3. So we have 27 of those. In each branch, how many empty containers do we have? So what's that? Yep, perfect. So if you remember the bag analogy, essentially when this says 0, 0, 0, it means there's a bag within a bag within a bag. Since all of these here share the first 2 zeros, it means all of them have 2 extra bags. So there's 14 items in each branch. So if we want to get rid of all the extra empty bags here out of flatten, graft, or simplify, which one should we use? What's that? It could be flatten, but not what we want. Yeah, it's simplify. So if we want to keep the branch structure, click simplify. It gets rid of all the extraneous branches. Now, if we want to combine these all into just one list, then it's flattened. So flatten here, now they're all in one list. So number 378. So what I'm going to do here is I'm going to double click on this exclamation mark. And what you need to do, so you can see there's a few things here. So there's RGBA colors. It can tell you the entire value of each pixel you sample. Red channel, green channel, blue channel, alpha, which is essentially its transparency, color hue, color saturation, or color brightness, which we are going to use since we have a grayscale image. Tile, clamp, flip, these are just ways it'll tile. And what we're going to do is we're going to set it up so it doesn't really work first, just so you can see why something's important, and then we'll fix it. But what you need to do is in your file path, you need to navigate to your file. So if I'm sampling this, if I have a picture frame of this pug in Rhino, but I'm sampling this, it's not going to matter that I chose that surface. It's going to sample this one. So I want to sample cute dog eyes.jpg. So okay, and now you can see the image actually pops up in Grasshopper as well. So now what we're gonna get, if we look out at what our data is, we get a bunch of numbers between 0 and 1. So 1 being white, 0 being black. Now, if you look at the amount of values we have in here, you can see how... Okay, another pop quiz. If the last number in a list is 377, so that's the index number there, how many values do we have in this list? Yeah, that's right. So 378. If we look at our points here, also last index number is 377, so we have 378 points. So we have one value for each point. They'll be in the same order as these points too, so that's what allows us to, you know, meaningfully create geometry out of this in relation to those points. So what we're going to do first is we are just going to maybe make some circles and color them and try to recreate this image in Grasshopper. So what we'll do is we'll go to, let's go to curve. So the curve tab here, primitive, and circle. So the circle, create a circle defined by a base plane and a radius. For your base plane of the circle, you can put in a point. If you do that, it's going to make this circle in relation to the XY plane. So you can see we have all these little circles, and what I'm going to do here is just by hand, I'm going to increase their radius, so you can see the second input is radius. I'm going to right click it. I'm going to set a number, and if that's 1, we can say about 4 for this. So that's fine. And maybe I'll increase the density of these circles just so we can see a little bit better. So it's like any image. It's like resolution in a JPEG image. The more points you have, the more you're going to be able to make out the image you're sampling. So that's why I'm just sort of moving these until I get a pretty dense field like this. So there we go. So I'll save the file. What I'm going to do is I'm going to make surfaces out of these circles just so we get a better view of what's going on. So I'm going to go to the surface tab, freeform, and then boundary surfaces. Putting that in. Boundary surfaces is easy, just one input, edge curves. Put that in there. Might take a second depending on how many circles you have. And now, if I'm going to turn off these points, we have a bunch of surfaces on our pug. Okay, so we have circles. We have corresponding values from 0 to 1. So we're going to use a component that we haven't used yet, but it's really cool for doing visualizations. If you go to parameters, first tab, input, and then gradient, so represents a multiple color gradient, put down there, you're going to get this little thing here. And essentially what this does is you're going to have a lower range of the gradient, you're going to have a higher limit of the gradient range, so, and then you'll have the value that you put in. So what happens if all these values are from 0 to 1? Our lower limit here is 0, our higher limit here is 1. Anything that falls, let's say 0, is going to be assigned this light pink. Anything's 1 is going to be assigned this darker red. And then, you know, values in between will be assigned color values in between corresponding to where they fall in the gradient. You can move these gradients around. You can add in extra colors. Or in this case, so I add in a purple. I'm just going to right click this little rainbow here, go to presets, and I'm just going to go white to black. So does anyone see anything kind of wrong, like what's going to happen to this image? So our range here is 0 to 1, white to black. In this image, our range is 0 to 1, black to white. So essentially, can anyone think of a simple non-grasshopper arithmetic way of inverting a number between 0 and 1? Okay, so the way you can do this, if you want to find like any number in a given range, if you subtract it from the upper end of that range, it's going to flip it. So think about this. If you have 0.5, middle of a range between 0 to 1, 1 minus 0.5 is 0.5. It'll stay the same. But if you have 0.25, 1 minus 0.25 is 0.75. Likewise, if you have 0, beginning of the range, 1 minus 0 is 1. So you see how that kind of flips everything? Kinda? Okay. What's that?
Oh, the computer is broken.
Okay, so for this, what I'll do is, like, let's say we have a range of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Multi-line data. So if we subtract all of these values, or we'll start with 0 actually. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we have all these values here, and we go to math, operators, subtraction, for our A input, we put 10, so the highest value in our range. So 10, commit changes, plug in B, or plug in our list of values for B. What we'll get out is the reversal of this list. See, because 10 minus 0 is 10, 10 minus 1 is 9, 10 minus 2 is 8, 10 minus 3 is 7, and so on. So that's what I mean inverting the list. So if you subtract a list of values from 0 to 1, from 1, you'll get the inverse. So to fix this, we can go to math again. Where is that? Operators, subtraction. Since we know the highest value here is 1. For A, we can right-click it, set data item 1, commit changes, plug the points into B, so the values rather, and then now the output of this, we can just plug into T. So that's assigning them a color on this gradient based on their value there. So now all we have to do to sort of see this, so this is kind of a fun step, is go to display, preview, and then custom preview. So our geometry, so it has two inputs, geometry to preview, the shader override. So the shader one is our gradient here. Our geometry is our surfaces. Now let's see what we got. I raise a hand, who thinks this looks like a pug? Yeah. So what happened there? Essentially what happened here, if we increase our points, we're seeing some weird thing happening. It looks like something's repeating, right? And it is. So okay, I'm gonna go back to like 25. So essentially the reason why this isn't working and we don't have our cute pug before us, we'll just increase that, is if we go back into image sampler. So let's double click on image sampler. Our X domain and our Y domain here are both 0 to 1. So what does that mean? Remember how I said if you add a pug image here in Rhino, but you were referencing that topo image, Grasshopper is still going to reference that topo image? In the same way, even though this surface here and these points here have a domain of, let's say, 0 to 200 in the X direction and 0 to, let's say, 100 in the Y direction, since the image sampler is still getting 0 to 1 for its X domain, 0 to 1 for its Y domain, it's tiling all these pug images across. So in here we probably have like, 100 tiny little pugs. Since our resolution's pretty low, we can't make them out. If we said tile set to clamp, you'd see that what would happen is it's gonna sample in one corner probably, so somewhere in there, and the rest is just gonna be white. So we'll set back to tile, and then we'll figure out what our domain has to be here. So I'm gonna hide this. So you can see that sometimes there's this little Mona Lisa icon there. What this does is it takes the aspect ratio of your actual image. So this image here it's 1920 by 1080. Whew, so perfect desktop size for anyone if they're interested. So it's laying it out so you can see 1 to 1920, 1 to 1080. That's not what we want though. So to fix this, what we can do is we can just figure out the domain of these points here. Now to do this, we have a bunch of points. They have X, Y, and Z values. We can deconstruct these points. So we can go to vector, point, deconstruct. So you can see the input for deconstruct is input point. Now the outputs, we're getting all the X values and all the Y values. And then to find the domain of these, we can simply go to math, domain, and then bounds. So create a numeric domain which encompasses a list of numbers. So that's going to give us essentially the bounds of this list. So for our X, we'll plug it in. I'm just going to copy this bounds, or else I'll just review it. So math, domain, bounds. So we're going to plug Y into bounds as well. And we essentially just want to see what these bounds are, because unfortunately, we need to type them in here. It's kind of strange that it doesn't have the ability to take in bounds, but that's how it goes. It doesn't mean we can't scale this after. It's just at this first step, we need to put in the bounds by hand. So to do that, what I'm going to do is I'm going to grab two panels. So I'm going to go to params, input, panel. So these guys, they should be familiar by now. I'm going to just copy it. So Control C, Control V, and then I'm just going to take our X bounds, plug it into here, and our Y bounds. So it doesn't matter. I actually didn't follow my own advice by placing this image at the 0 axis in one corner. I guess I was overwhelmed by the pug. But it doesn't really matter because we can copy this. So essentially what you can do if you want to copy data from a clipboard, so we know these are our X bounds. If you want to just keep it straight for later on, we can right click it, give this list a title, X bounds. We can right click this one down here, give it a title, Y bounds. And that's just so if we return to this file in the future, we know what's going on. So to copy our X bounds, what you can do with any panel is you can right click it and go to copy data only. So now the reason why you want to copy data only is, let's see, so if we right click and go copy all content, we double click into this panel, hit this, you see what happens is it's going to copy our path as well as our index where we just want the domain itself. So if we right click and go copy data only, you can see it just gives us that domain. So that's what we want for this. So again, right click, copy data only, double click your image sampler here. Our X domain, we're just gonna Control V, paste that in. So okay. And now you can see something's starting to happen. It looks like there's more white in the center, so it looks like it's building up white in the center, but we have to copy our Y bounds as well. So I'm gonna right click this, copy data only, double click our image sampler and set our Y domain as that. And then look at that. Pile of circles. Kind of looks like a pug. So for this, you know, if you really want to go for that pug aesthetic, what we can do, so again, you can abstract something. We can just increase the density of our pixels. So like an image, it doesn't matter now that we have our domain, it's all good. So let's increase this to 40. So if you have a lot of points, it might freeze. Has anyone had any fun with like a freezing computer while working with Grasshopper? Yeah. What's that? Yeah, it happens. Yeah, patience is a virtue. I spent all yesterday setting up this solar analysis, so it's like analyzing 120 apartments, iterating through 10 variations of windows for each unit. Set it up, let it go. It took 9 hours to go. I woke up this morning and I was like, oh yes, it looks awesome. And then I realized that the building rotated 90 degrees in the wrong way. So it's all just like moot. Yeah, so that's gonna go. Sometimes when it auto saves at the same time you're updating something, that happens. But let's see if we can get that explosion. No. I'm actually bummed out that I've never been able to get this happen in class. Anyone have any questions? Oh, it's if you go to display, the display tab there, and then under there it should be the custom preview. Yeah. Okay. Well, that's fine. Does anyone else have any questions? Because we'll go on to using geometry.
The images we brought in, even after we put it on the desktop, are still not like I saw that today.
Image sampler worked?
No, I mean initially when we
Yeah.
brought the image in and it was white.
Yeah.
So we tried grabbing an image and putting it on the desktop and it still was white, but I did all this stuff and
It works in
generate
image
it
sampler.
anyways, I just can't see it.
That's strange.
Yeah.
We can try figuring that out
I know,
after.
after it.
It might be the direction of the surface, maybe. Okay. So a lot of the times, that's why you save often. That's fine. Luckily, I saved this file. So, oh. Okay. So Grasshopper is sometimes good at giving you a recovery file. Fingers crossed it is. It doesn't really matter for this, just, yeah, save a lot. Okay, so we are in Dropbox, DM2, lecture files, yeah, like this. So usually you want to go open recovery file, and look at that, back to where we were. Except our sampling isn't right, but we can just copy that quickly. So copy data only. Okay, so we have this cute pug here. We want to make a monument to this pug. So the next thing we can kind of do with image sampling is we can base actual geometry. So this is all, you know, well and nice that we can, you know, essentially recreate this image in Grasshopper, but as all of us spatial designers, we want something that deals a little bit with space. So what we can do is we can take these values and use them to define something else. And really they can define anything. So in this case, let's say we have these boundary circles. What we are going to do is we are going to extrude these up based on this. So if we have a range from 0 to 1, I'm gonna just extrude these up and see how it works. So we need to grab a vector. So we can go to vector, vector unit z. So again, this is the up direction. Now what happens if we plug our image sampler into the vector here is these all have a direction of up, but you can see now their amplitude, so how far they go, are different. So the first one's 0.2, second one's 0.2, but the third one's 0.13, so it's a little bit shorter. Now if we extrude these boundary surfaces, so we can go to surface, freeform, extrude. So extrude works the same way as Rhino. So profile, curve, or surface, put those in there. Extrusion direction, we can put the vector there. And now you can see something that's not very cool, really. Now there's a few things here. The first thing is that let's say we want these all to be solid. So if we look through this list out of this, we see a bunch of closed B-reps. That's fine, that's what we want. So a closed B-rep is this like 3-dimensional object. But here at number 9, we see a trimmed surface, so that means it's flat. It's not 3-dimensional, it's still just this 2-dimensional surface. Does anyone have any idea why that is?
It's either absolute white or absolute black.
Yeah, exactly. So it had a value of 0. So if you take a surface, extrude it 0 units, it's not going to extrude at all. So in order to fix this, we can sort of, you know, come up with a little bit of arithmetic to help us out. So we're actually going to make a little custom component here. I think now is probably a good time to see this. So what we're going to do is we're going to go to Math, Script, and then Expression. Oh, no, wrong one. Sorry. Math, Script, Evaluate. Now, so we have f, x, y, that looks good. What we're going to do is we're going to grab a number slider. So parameters, input, number slider. And we're going to use this number slider as a scale. So we're going to say, you know, everything times, it could be 0.25 to everything times, let's say, we can sort of change in here, everything times 250. Now, what's wrong with having 0 is our minimum for this slider? So 0, if we were going to multiply all of these things by a factor and it was a factor of 0, they'd all be 0. So we just want to put in something that's really small. So how about 0.001? At least that gives us something. So 0.001, so you can see that's the lowest, all the way to 250. So I'm going to plug this into y, and we're going to plug our values from the image sampler into x. And now we're going to take the r, so the result, and plug it into the vector, and then we get an error. So the reason why we get this error is because right now this expression here is doing nothing. We need to define what this does. So to do so, we can double click on it, and then up is going to pop this expression designer. So you can see here it tells you your variables, so in this case x and y, and it just uses common notation. So in this case, what we want to do, if we want to avoid a 0 here, we can simply go x times, use lowercase, x times y plus 0.1. Now if everything's good, it's going to say no syntax errors detected in this expression. Hit OK. And now you can see that the expression does something. So now we have a abstracted version of a pug. Now, what would be amazing is that if, let's say, you were presenting this in some sort of outdoor public space project and you said all of these are defined by a solar analysis and wind analysis, but secretly you knew that it was just a pug. So yeah, if anyone sees my final thesis presentation this year, just be aware, no matter what I say, it's all just a pug. Okay, so we have this. So that's one thing we can do with geometry. So I think what we can do now that we have this, I'm going to show a little bit more of a practical example of something you could do. Even though a pug's pretty cool, I'm going to show you just like a little workflow that we can work out. So does anyone have any questions about this before we continue? I'll save it. If anyone's computer's frozen, just close the window, let Rhino freeze, and then I've saved this. So it's in Dropbox so you can catch up. So what I'm going to do now is I think, so essentially what I'm just thinking how to do is to essentially take something you sketch and turn it into, let's say, a computer, like an actual plan sort of thing. So there's a lot of ways to do this, but in this case, we're just going to make some sort of path and we're going to have these mountainous elements around it. So essentially what I'm saying here is, let's say you have a square like this. So I'm just going to draw a square like this. So we're just going to save all this. I'm going to disable it just so it doesn't slow anything down. So we're designing a little park. We know we have a path going through said park. So here is our path. Like so. I'm just going to offset this. You don't have to on both sides. And I'm just going to trim these so they connect. Hit enter, and voila. So great. So we have this here, and let's say we want to create some interesting kind of topo around it. Now what you can do is kind of a workflow to quickly iterate through things, is to take this, set the background here, so display, background, minimize grasshopper, set it to a solid color, set the solid color to be white, like this. And now what we're going to do is we're going to view capture to clipboard. So whenever you type this in, always put a hyphen in first. So hyphen view capture to clipboard. Now the reason why you do the hyphen is it's going to give you some options. So whenever you put a hyphen in front of a command in the command line, it's going to give you options. So in this case, view capture settings, we have our width, height. We don't want to touch those, keep the aspect ratio the same, but scale here, we might want to scale this up maybe like 4 times. So dimension multiplier 4, going to hit enter. And then what that does is it just copies it to your clipboard. So in this case, I'm just going to open Photoshop. Also, if you're doing a Mac kind of setup where you have Photoshop on the Mac side and Rhino on the PC side, something like that, there is also another command, view capture to file. So hyphen view capture to file. It does the same thing, except you can save a file, copy it over to your Mac side, and work from there and sort of flip back and forth. But in this case, I can just go new in Photoshop. I'm going to paste that. So you can see it's actually pretty light here, but that's okay. I'm just going to go to image, adjustments, levels. I'm just going to really increase the darkness just so we can see what we're, just so we can see what we're doing. Like so. And then I'm also going to crop this image. So I just have a square image like this. So I'm just saying this image on multiply here so we can work on our background here and just see what's going on. So essentially now what you can do is if you leave this as a grayscale image, you can define topo. So in this case, this is good for like quick sketching. Like let's say we want a pond here. There's a nice pond. Maybe we don't want, you know, the transition to be that sudden. We can go like that. So essentially what I'm doing here is just by color, I'm defining elevation. So you could also do this for a surface or whatnot too, right? So in this case, now I'd suggest that you keep your hardness pretty low maybe. So there we have that. And maybe here we want like, so I'm just going to select this. Maybe we say white is like a peak. So I'm just going to select in here and in here. So I'm just going to say that like, you know, 50% black. So, okay, I'm saying it to 50. I'm going to make a new layer here as kind of the base. I guess what I can do actually is just paint this all across everywhere. Okay, so there's our base of our drawing. Oops. So we're going to set this to multiply. And then, you know, however you want to do this, I'm also going to make a peak, like a hill somewhere along here. It looks like a happy face. Okay, so there's our sweet topo. I'm going to turn off this layer here. Maybe I'm going to do one that's a little bit lighter at the top here. Okay. So there we have it. So I'm just going to save this as a JPEG. Save it on my desktop. So topo, like so. And now what we can do, we can go into Grasshopper. So we have the same setup here. We can, so I'm going to enable all this. I'm going to set a surface, so I'm just going to go to wireframe. Maybe shaded. I'm going to make a surface from here. So surface planar curves. I'm going to set this surface. So you can see it first. We're going to get like weird pug image because we're still sampling the pug. Control H. We get our bounds automatically. So I'm going to copy that in. So copy the X bounds. We get our Y bounds, so copy data only. So I'm going to copy in the Y bounds. And then now we can link to our topo file we made, like that. So it's still on brightness. Hit OK. And now what we're going to see, if we go into perspective, is we get, so you can see it quite well there, huh? this image, so there is our, oh yeah, and we, you know, we've covered our path. It doesn't really matter. We can take that out. So let's say in this image, we're like, oh no, we covered our path. Like that's no good. Essentially now what we can do is we can update this really quickly, set this to 50, or I guess we'll set it to black for 0. However you want to do this. Trace in our path. Save the JPEG again. So topo, save. Okay, apparently you can't save over it, which is a shame. We can just save as 2. Topo 2. It'll turn into this thing where it's like topo 2, final. So hit OK. Go back into grasshopper, so we can just update this then. So topo 2, hit OK, and there we go. We've made a clearing for our path. So this is just a way that for surfaces, so we'll get into more applications for this, but just know that you can use this sort of technique to easily manipulate geometry in Photoshop, really. Doing 2D to 3D, it's a really fast way of working. So anyone have any questions about that? No? Okay, let's take a 10-minute break. Oh, sure, yeah. So I'll actually maximize this so you guys can see it. Maybe I'll condense everything to make it a little bit. So essentially assignment 2, which I'll sort of cover at the end of class, is this. It's taking an image and making interesting geometry out of it. So again, it's going to be due on Monday. So another pretty close deadline, but it's, again, a small assignment, so it's not too bad. There we go. So one thing I like about images and working with images, I'll just say, is that so many things are presented in, you know, graphical representation in design, be it from structural analysis, you think of like your standard blue to red, thermal analysis, like blue to red again. Topo can be represented in black to white lots of the times. There's so many things that architecture and landscape architecture deals with that's displayed in a gradation of colors. And that's why it's something that personally I've incorporated into a lot of my work and research, is just like using colors, like very simple JPEGs and whatnot, to make really complex and accurate geometry. So one thing I can think of is the OMA CCTV tower, of course. So their facade done by Front Architecture. Here you can see how at its most basic, so of course it's, you know, I'm not sure if this is compressive or tensile, but essentially you can see how the thickness corresponds to, of course, the stress that goes through the given member. So purple being the least amount, so you have very light structure there, to red, and of course there's other factors here, but you could, if you want to mock this up for a project, do that same sort of analysis and base your structure on the colors that the FEA program outputs. So, you know, without even knowing a lot about structures at that level, it's like you can just do something that looks convincing, or thermal or solar or anything like that. So that's just why, like, I think this stuff's actually super useful. And even though we're sampling pugs, just think about all the applications you can use this for. To something that we can kind of play around with a little bit more. So I'm going to change it to a square. So all we're going to do is we're just going to delete this circle. like so. And instead of the circle, we are going to go to curve, primitive, rectangle. So like that, and we're going to put our points in. Again, rectangles have domains, like so. And you know what we're going to do, just for fun, is we're going to figure out how to make these rectangles the exact size they need to be, or so they vary based on this surface. So can anyone think of how we might go about creating rectangles that are the right size for this surface, so like they sort of move along as we increase the slider? So we have the overall, so essentially what I'm thinking is we have the overall bounds here, and we have the amount of rectangles that stretch across it. So if we just divide sort of the boundary by the amount of rectangles, that should give us a good size for our rectangles in the X and Y direction. So to do that, what we might want to do is we can go to math, domain, and we can go to deconstruct domain. And we're going to deconstruct both our X domain and our Y domain.
There's so many parts with the construct domain.
So there should be construct domain, which is the opposite. It allows us deconstruct domain, and there's also deconstruct domain squared, as well as deconstruct domain squared, which is another one of those. But we're just looking at the top one here. Can you see this one, deconstruct domain? Yeah. So we'll use that, deconstruct domain. And essentially this is just going to give us the start of our X domain, the end of our X domain, the start of our Y domain, the end of our Y domain. And we just want to find the difference between these two values. So we're going to go to operators, subtraction. We're going to need two of these. So again, that's under math, operators, subtraction. Now what we want to do is we just want to plug the start and the end into A and B. And you can see we have our start end domain here. Now you can actually see they're the same because we have a square. That's fine. Now one thing we can do is, you see here, so the way, again, this is like one of those just simple arithmetic things. Think about 1 minus 2. What's it going to give you? -1. What's 2 minus 1? It's 1. So it's always going to give you the inverse. So you're always going to get the same number when you subtract one number from another. It's just going to be negative or positive. So likewise, in the start end, if we mix these up, you can see we get the same number, 449, except it's positive. So you could just by hand, switch those wires to always get the positive number. Or a really useful component you can use is the absolute. So it just takes the absolute of a number. So that means it's going to return the positive value for either a positive or a negative number. So that's under math, operators, absolute. So we'll want two of those. So now whatever we put in here, we're always going to get a positive number. So now we have this here. So now what we want to do, since we have the absolute, is we just want to divide these by the U count and the V count. So, and that's going to give us the width of the rectangles here. So that sort of makes sense. We're grabbing the overall domains and then we're dividing them by the amount of sections we have. So to do that, we can go to Operators, Division. I'm going to grab two of these, so I just Control-C, Control-V. We're going to plug our absolute domain into A. That's what we're dividing. Our absolute domain for Y will plug into A as well. And then for B, we'll plug in our U count and our V count. And now we get two values. So this is the width of our rectangles and the height of our rectangles. So anyone have any questions about any of that?
So when I open the file, one of the evaluate was red. When I like open the grasshopper phone, you can go from someone like shoot.
Okay, if the evaluate's red, it might be sometimes, like I've noticed that for some reason, if you double click it, what's the expression?
It says expression generating error for x, y, left-hand value operator, asterisk is null.
Left-hand operator asterisk is null. Does your expression look the same as that?
Yeah. Yeah.
Oh, is that? I wonder if this is yours also giving you an error?
Yeah, it says left-hand value operator is null.
Okay, so that probably means that something coming through here is strange. I'm gonna see this. Let's see what you put there. Yeah. Oh, no values from one source. Your sampler. Okay, so that's linked. What happens if we try to relink to this? Yeah, so it's probably because your image sampler isn't outputting anything. So if your image sampler isn't outputting anything, maybe try relinking to it. Does that work for you? Okay, we'll figure that out after class. You know that like military expression, no man left behind? Sorry, we got a time constraint. Just, yeah, follow along, it's recorded. Sit back, enjoy. So now we have these rectangles. So we have these two boundaries here. Now, since we know for a rectangle, if we look at this, we need a boundary, so like -1 to 1 or -2 to 2. Essentially what we want to do is just take these here and divide them by 2. So these boundaries here, we're going to divide them by 2. So I just copied that after I put in. The reason why we do that is, think about if we have a rectangle that has a width of 2, if we divide 2 by 2, we get 1 and 1. So we can say -1 to 1. Does that sort of make sense why we're dividing that by 2? We're essentially centering it on the origin. And now, after all of this, we can make our new domains for our rectangle. So instead of this time deconstructing domains, we're going to use construct domain. So we're going to go to math, domain, construct domain. So what we're going to do for this is for our A, we're going to put in an expression. Expression, what do you guys think the expression is going to be? So if we're dividing, let's say our rectangle's too wide, we're dividing it by 2 to get 1. Our domain needs to be -1, so we can put in negative x. Oops. So we put in negative x for our domain. So negative x for the first one, and then the second one we can just leave it as is. So now we plug in our division like that into both. I'm just going to copy this component, put in both for that. So now what we can do is we have these rectangles. We can plug in our domain in the x direction. See, now it fits perfectly. And if we adjust this, you can see that it moves with it. So that's nice. And now for our y, we're going to put in the same. So now we have a parametric bunch of rectangles. So does anyone have any questions about those steps? Hear lots of what? Okay, so essentially the last component here, so you're asking about the domain. So essentially what we're doing is, so you guys understand how we take the overall range of this domain. Like let's say this is -10 to 10. We're subtracting -10 from 10 to get 20, so the overall width, overall length. So that's what we're doing right here. So that, I'm going to group this, is getting the overall length. Now what we're doing is we're dividing that overall length by the amount of rectangles we have. We know we get that from the slider. So that takes that overall length. Let's say overall length is 10. We have 10 rectangles. Then we're going to get 1 for the width of each rectangle. And then what we need to do here is, if you think of each, I'll draw this before. So the domain in grasshopper, if the width of the rectangle is 2, and let's say in this direction it's 4. So we have a rectangle that looks like this. To center it on the point we want, since the rectangle is based off its center point, we need to divide this by 2. So 2 divided by 2 equals 1. So we can say this point here is -1 in relation to this point. This point here is 1 in the x direction. In the y direction, we divide 4 by 2 to get 2 here, -2 down here. So that's why we divide that. So that's this division right here. And then so the last thing we do here, and I'll redo this, the last thing we do right there is, so we have this divided thing, so it's like dividing the 2 or dividing the 4. To reconstruct our domain, we go to Math, Domain, Construct Domain. Now, if we were to just plug these widths right into this component, you're going to see we're not going to get anything here. So if we plug this into the rectangles, we're going to get infinitely thin rectangles. Same if we do that for y. If we do the same for the y, so take this division here, plug into the y, put that in as our rectangle's y component, we're going to get just little dots. And the reason why is these domains, you can see it says 6.4 to 6.4, so that's 0 wide. This one here says 6.6 to 6.6, so it's 0 wide. So instead what we can do is take the beginning of this domain, go expression, -x, so that's like making the -1 up there. And now you can see we have the right width. Same with the y. We can go expression, -x. And now we have the right height for our rectangles as well. So once we have this, all these rectangles, we can just plug into the boundary surface component we had made before and see what happens. So I'll let everyone catch up while my computer thinks. Any other questions I can... Okay, so look at that. So now we have a pixelated version of this path. It's like a, look, I'm PRK angles. Okay, so what I'm gonna do here is I'm actually just gonna decrease the resolution of this just so it's a little bit easier to work with. So a lot of the times when I'm doing something where my computer is sort of slowing down, I'll do a small part. So like yesterday I said I was doing that solar analysis for 120 units. Did I test on 120 units? No, I test on 1. Once it worked on 1, I test on 10. Once I worked on 10, then I let it go by itself and went to bed. So sort of test in small groups. So in this case, I'm going to lock the solver, set my U count to be, you know, I'll say 10 by 10. So 10 by 10. I'm going to unlock. You can see it goes much faster, but we still get what we want. So that's good. Okay, so now what we're going to do is we're going to sort of do another transformation based on this geometry. So we could image sample something else, but I think instead what I want to do for this is, let's say all of these want to twist towards a certain point. Essentially, we're going to take each of these rectangles and twist it towards a point here. So for each of these rectangles, I'm going to grab a face. So we can go to Surface, Analysis, Deconstruct BRep. Plug that in. So now we just get a bunch of faces. So you can see here that now I'm going to simplify this just so we don't have the extraneous branches. We have 125 branches, so 1 for each BRep here. And if we look in the faces, we have 6 items in each list, and that makes sense because any rectangular prism has 6 faces, 4 on the side, 1 top, 1 bottom. So I'll preview those off. What I want to do is, let's say we want to twist them all so they're looking at a point, you know, but let's sort of put a little sphere here. We can say this is the sun or something. It's just the direction we want to twist all these faces towards. What we can do is we can go to list item out of these faces. So set, list, list item. Plug this in here. And it's going to give us just one face of all of these rectangles, or these rectangular prisms. Now, with this, since all these rectangles are the same, like they are made in the same way, they're all probably going to have the same configuration of faces. So we know with list item, the first input is list. The second input is the index, so which item in that list you want. And the third input is wrap. So remember that wraps the list around. So if we click on the little plus here, we can see which face is which. So we can see that index 0 or index 1 of all these lists is this face. So we can say if Y is north, we can say the south face. Index 2 is, we can say never eat soggy wieners, the west face. So what I want to do is I want to take all these west faces and twist them towards this sun here. And then what I'm going to do is I'm going to loft that geometry to create these twisted spires that are facing wherever this object is. So since I know it's 2 by just sort of clicking through there, what I can do is I can minimize those little tabs, and under I, instead of the default 0, I can just go to, so I right-clicked I, go to set integer, and instead of 0, I'm just going to type in 2, commit changes. Now this just gives us all of these faces. Perfect. So essentially, what we want to do, so we know the amount that we want to twist these faces, is, so this is just, again, one of those times where we think of an algorithm. Maybe I'll zoom out so you guys can see what's going on if you want to catch up. I'll also just save the file right now. So this is one of those times where we just want to like think about how we would do this. So let's say you got, so here's a person, here's grasshopper, your really dumb friend. That's their nose, there's their glasses, and here's you, and you're telling them something. So that's a word by way. So these are your commands. And then over here, there's a car that's heading straight towards them. Or a giant, like, cyclops dog, or whatever this is. There's something like heading towards them. And you want to say, and here's the very front point of that, you want to say, hey, turn your head this way. But again, grasshopper being a big dummy needs very explicit steps. What do you think you could tell him, or what information do you need to give them for them to turn their head exactly to this point, thinking that they're originally looking this direction?
An angle.
Yeah, you have to give them an angle. So here's our angle. And how do you get that angle? So what you could say, and I guess the analogy kind of breaks down here, but you can say, hey, you're looking in exactly this direction. Imagine, and I've never said this to a friend, but imagine the normal vector shooting out of your nose. You want to take that vector and you want to find the angle between that, the center of your head, and a car that's in the distance. And again, this is where it sort of breaks down, because all of a sudden this person has to be able to, out of their periphery, calculate this angle, but computers can do that quite well. So that's how we're going to do it. And then from there, we can say, okay, twist your neck that way. Honestly, when you think about, like, you know, the steps that programs need in computers, it just makes, like, day-to-day life seem so, I won't get too deep, but it makes it seem like rather impressive, or rather frustrating to try to program, like, you know, simple things. Okay, so we have these faces. We're going to find their normals. So this is easy enough. We're going to go to surface, analysis, evaluate surface. We're going to plug in these surfaces. So that's surface, analysis, evaluate surface. Now, for our UV, so you guys remember what the UV grid on a surface is? It's the grid localized in that surface. What we can do is these surfaces, we don't know what their grid's set at. It could be like negative 100 to 100 or something like that. But if you right-click the S input, and you can do this for curves as well, right-click it and hit reparameterize. Essentially what this is going to do is it's going to reset the UV grid of all these surfaces to 0 to 1. And the reason why that's really easy, or that's really useful, if we set its UV grid to 0 to 1, now we can right click our UV, go to set 1 point, and then we can just type in 0.5, which is the center, comma 0.5, enter, and now that automatically gives us the center point and plane and normal of all those surfaces. So we have that. That's great. We have this normal vector. What we can do is we can deconstruct these vectors to find out their angle, because we don't really want to take into account the difference in height. We don't want to, you know, figure out how high up this sun is compared to these, because we just want to keep the twisting linear. So in order to do that, we're going to deconstruct the vectors. So we'll go to vector, vector, deconstruct vector. So we have our x values, our y values, our z values. And what we're going to do is we're going to go to, do you guys remember that little trick we did when we flattened a point onto the xy plane by just removing its z value? We're going to do, we did that. It's in YouTube, so we're going to do the same thing. So imagine if it, let's say a vector is composed of 3 values. So it goes, you know, 1 unit to the right, so x equals 1, 1 unit up, so y equals 1, and 1 unit like vertically up, so z equals 1. If we deconstruct that vector, we're going to get 1, 1, 1, right? Now, if we go to vector x, y, z, so vector, vector, vector x, y, z, essentially what we're going to do is we're going to plug in, you can see the default here is 0. If we plug in the x, 1, plug in the y, 1, but we leave this z default, it's going to be 0. So that essentially flattens that vector in regards to its height. So we have one vector, that's great. Now the other vector we need, so what I'm going to do is I'm going to now reference this sphere. So if you hadn't made a sphere in Rhino, maybe just go to your standard primitives here, and then go to sphere, like so. I'm going to reference that sphere in Grasshopper now. So I'm going to go to parameters, geometry, and then brep. I'm going to set one brep. There's our sphere. I'm going to find the center of it. Anyone remember the command for finding the center of something? I'll give you a hint, it's under surface. Yeah, it's actually, so we can do surface area. For this, it's going to give us something. It's, in this case, actually will give us the center. For a 3D object, you probably want to use volume. So same thing as area, but yeah, that's perfect. So we'll use volume, find the centroid of the geometry. And now what we're going to do is we're going to go to vector 2 points between all of these points here. So all these planes here, we're going to find the vector between them in this center point here. So we're going to go to vector, vector, and then vector 2 point here. So create a vector between 2 points. Now, if you remember, when we evaluate our surface, so that's this component here for all these surfaces, we have 3 outputs that come from the evaluate surface. So the first is the point at UV, so at 0.5, 0.5, the center. Next is our normal vector, which we already grabbed there. The third is the frame, so that's this little plane you see there. We want the point for this, so we're going to take the point from evaluate surface. We're going to plug it into our A for our vector 2 point. You'll notice that this wire here is dashed. What does that mean? were those words?
Is there multiple branches?
Exactly, yeah. So there's multiple branches, multiple lists. So our volume, we have our center point here. We can plug that into B. And see, now this is one of the times when data management, it's good to understand how it works. So if we have multiple branches here, one with each item, here we just have one item. If these were both flattened, both one list, it might give us a weird matching, right? It might just do shortest list, connect one to one and leave the rest blank, or it might disorganize our stuff. But since we have here one list for each item, we know it's going to match each item up with this 1 point, no problem. So we have some vectors here. We want to do the same thing, deconstruct these vectors, recombine them without the Z. So I'm just going to grab these two components we already have here. Maybe I'll just review it. You could just grab these two components, copy them, you know, reuse them. But to rebuild that, we can go to vector, vector, deconstruct vector. So again, that's just taking these vectors here, breaking them down into their X, Y, and Z components. And then now we go to vector, 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 X, Y, Z. And we'll plug in the X, keeping it. So if it was 1, we'd get 1. We'd plug in the Y, keeping the Y. So if it was 1, we'd keep the Y. And if the Z was 1, we don't plug in, then Z becomes 0. So it flans the vector. So now if we look at what we have, because we're paying attention to data management, you can see here we have 121 values. So these are the vectors normal. So your friend looking that way. 121 vectors, each in their own branch. Here you can see we have 121 vectors, each in their own branch. This is the vector between your friend's head and the car. So since we have that same data pattern, we know we're safe. This is going to work out. So to do that, essentially what we can do is we can find the angle between these two vectors. So vector, vector, angle, compute the angle between two vectors. So first vector is here, the second vector is there. Optional plane for 2D angle. We can leave that blank because it's just the world XY plane. And then now we're going to be given an angle in radians, or an angle, or the reflex angle. So if you guys remember what a reflex angle is from basic geometry. So reflex angle, let's say you have an angle and it's like, you know, 30-ish degrees. The reflex angle is going to be the 330 degrees. So that's all a reflex angle is. Radians, do you guys know what radians are? It's another way of describing, so if you think of a circumference of a circle is 2 pi, you can describe it as, you know, angles is a smaller bit of pi. So like, for example, 90 degrees I think is pi over 2. 180 degrees is pi. I just always convert them to degrees because I don't think in radians. Or I just kind of ignore them, or try to. But in this case, what we're going to do is we're just going to take, so remember how we have all these faces here? We're going to click plus to find the top face. Okay, so there we found the top faces of all these guys. So that's 3. Or is that the bottom? Maybe we should just do this the proper way. Okay. So we have all our B reps here. Actually, I know how we can do this. So we have all our B reps here, so our untwisted rectangles. What we're going to do is we want to twist the top part of it, leave the bottom the same, and then we'll loft between those two things. So to do that, we want to find the top rectangle and the bottom rectangle. So we'll take our original extrusions here. So that's, if you go back in your definition, it's right after the image sampler, this vector here. So it's the extrusions. Make sure that when you click it, you get your whole rectangles. What we're going to do is we're going to go to Surface, Analysis, BREP Edges. So I'll preview that off. And now, oh, that doesn't work. Okay. So there's a lot of ways to do things in Grasshopper. What I'm going to do is I'm going to go back to the whole faces thing. So we'll just redo the faces here just so it's easy enough. So from these extrusions, we're going to go to Analysis, Deconstruct BREP. Okay, that's perfect. So I'm just going to bring this to the front. I'm going to preview off all of this stuff except for that Deconstruct BREP that we have there. So what we essentially want is we want the bottom face, the top face. So to grab items from a list, what component should we use? It's under set. Is there a list? Yeah, list item. So if we plug the faces into list item, let's preview this off. You can see that list the index 0 gives us the bottom face. We can keep on clicking this till we find the top face. And it looks like index 5 gives us the top face. So that's fine. We'll just preview that off. And we'll grab. So if sometimes if you just want to like do this the easy way, you can just click until you find the things you want, preview it off, and then if there are surfaces, just grab 2 of these surface inputs. So parameters, geometry, surface. And then just plug the first one, so there's our bottom, so we can see it. Top one, 5 into another surface. So now we see that. So that's good. And now we just want to twist these top surfaces. So these here. So now we have our angle here. We want to twist them around their midpoint. So why don't we go to, again, to find our midpoint of a surface, we can go to Surface, Analysis, Area. Finds our midpoint of the surface. We have our angle there. So the last thing we want to do is transform. Euclidean. Rotate. So rotates an object in the plane. Our geometry is going to be our surfaces. Our angle, so rotation angle and radians. Even though we don't like radians, we have them. Works out well for us here. So let's just plug that angle into there. So you can see that they're rotating out in this crazy manner. The reason why they're rotating out in that manner is because we haven't put in our center point. So if we put in our center points for planes, now you can see they all rotate in relation to this sphere here. So why don't I actually preview off that, preview off that. You can see if I move around this sphere, they're going to move with it. So that's kind of neat. Now, the last thing we need to do is just loft between these 2 surfaces, and then we're good to go. So we can go, we have our bottom surface, our top surface, and then we can go to Surface, Freeform, Loft, our curves here. So we make sure our data is the same, so 0, 1, 0, 0 to 0, 120. We can simplify this if we just want to keep it 0 to 120 for our branches. Geometry here, 0, 0 to 0, 120. We can simplify it to keep it 0 to 120. Since those match up, if we plug them in, you can see now we get a bunch of twisted surfaces. Yeah, so that works. These surfaces aren't capped. And also, right now, they're like much too big. So maybe it's something we can change in our domain. So in our domain, if these surfaces are too big, we can set our domain to expression negative x times 0.5, let's say. B, we can expression x times 0.5. So you can see they're getting smaller in that direction. We can change our domain in the y direction too. So expression negative x times 0.5. And in this direction, expression x times 0.5. And finally, we can cap these loft surfaces. So to cap a surface, it's on our surface, utilities, cap holes. And there we go. We have some capped surfaces which twist in relation to a sun. The path, which may or may not be based off of a pug, and some kind of interesting geometry. So I'll save that. I know we kind of rushed in the end to finish there, but review this file. Does anyone have any questions?